Okay, so before we can get too far into elements and compounds and things like that, you do need to understand the atom. So let's talk about its structure. So modern atomic theory, these are the kind of central conclusions that, as of right now, we hold to be true regarding atoms. All matter is composed of atoms, so atoms are the smallest subunit of pretty much everything. All atoms cannot be subdivided, created, or destroyed in ordinary chemical reactions. Okay, so like you can't light something on fire and separate out its, electrons from its protons. Okay, however, there are things called nuclear reactions that we can do that with. Atoms of any element have a characteristic mass. And that mass is always unique to that element. No two elements have the same average mass. There's also the fact that atoms of any one element differ in properties compared to any other element. And that is because, oxygen has different boiling points than nitrogen, and carbon has a different melting point than hydrogen. No two atoms or elements can have the same chemical and physical properties. Right? There may be one or two somewhere that are the same as something else, but it's never all of them. Okay? So, a couple of important experiments that led to a lot of our discoveries and understanding of atoms are J.J. Thomson and his cathode ray tube. Right? This is shown down below. If you apply a high voltage to this tube that has some particular gaseous element in it, like hydrogen or neon or something like that, you can make certain things happen. Right? And through this experiment, we actually discovered the electron. Some of the major conclusions we were able to take from Thomson's experiment was that a cathode ray, when made with different elements, still has the same properties. Okay? Because those cathode ray properties stay the same, then elements must contain identically charged electrons, meaning there aren't some electrons that are more negative than others. They all have the same exact negative charge. Okay? Also discovered that overall atoms are neutral. All right? So since we were able to detect the negative charge, somewhere there must be a positive charge. And then electrons have so little mass that we actually consider it to be negligible to the other particles found in the atom. Okay, so really we think about electrons as having no mass. It'd be one thing like saying, we'll talk about that a little more. So after Thomson's studies, this was the atomic model, that the atom was this pudding, okay, this kind of massive thing that was mostly positive charge and then had these little specks of negative charge. Okay, and they were kind of stuck in the pudding. All right, so this was kind of like the first model of the atom. Later, someone named Rutherford holds an experiment shooting a particle at a gold, like a very, very thin gold sheet. So you can see the atoms of the gold, how they're lined up, and there's space for them to get through. The details of this experiment you don't need to know a lot of, but you can see that most arrows go straight through. A few of them are deflected slightly, and then some, but very few, are deflected greatly. Okay, so the conclusions because of that, the fact that most things were able to get through meant that the nucleus is very tiny because it's not hitting the particles. The particles are able to pass through, the electron cloud. The fact that when things did hit the nucleus, that they deflected, implies that it was dense, meaning that, it didn't break it apart. It was very compacted, tight together. All right, and then we were also to be able to tell that it was positively charged because these particles were positive as well, and they were deflected. Okay. Rutherford's finding, we were able to come to what is now considered what we use now, for the most part, as our atomic model theory, is that we have a central nucleus that has the positive and the neutral charges. You can't really read that. Let me make this bigger. So positive and neutral particles. And then on the outside, there is this vast electron cloud, which is not dense and very spread out. Okay? There's more details to this, but we will talk about that more a little later. The electron has a -1 charge. We consider the mass to be 0 because when we say proton and neutron are 1, that makes the mass of an electron like a millionth of it. And that's just, it's not big enough to impact any sort of equation or information that we work with, at least not to the precision that we are capable of today. So, and then the electron is on the outside in the electron cloud. Protons have charge of +1, a mass of 1, and are found in the nucleus. And then neutrons are neutral, so they have no charge, but they also have a mass of 1, so protons and neutrons are equal to each other in mass, and they're both found in the nucleus. Okay, so the massive part of the atom is the nucleus. So, a couple of key terms that we use for identifying atoms and elements is first the atomic number. So if you're looking at a periodic table, and find these numbers, 6, 15, 79. All right, you're looking at the big number in the left-hand corner, okay, left-hand upper corner, and if you find those numbers, you'll see that 6 leads you to carbon, 15 leads you to phosphorus, 79 leads you to Au, gold, okay? Now, the reason why we use these numbers to identify them is because the atomic number represents the number of protons found in each of these elements. All right, the number of protons determines the element. If something has 6 protons, it is carbon, regardless of the number of anything else. Okay, if something has 15 protons, it is considered phosphorus, regardless of the numbers of neutrons or electrons. Okay. Another identifiable number is the mass number, though this one isn't as constant as the atomic number, but each atom or type of element has its own specific mass. All right, so let's fill out this table. We have, our first one is oxygen. We aren't given the proton number, but we can find oxygen pretty easily on the periodic table. So if you find it, it's written down next to 8. All right, so 8 is the atomic number, which also happens to be our proton number. Okay, now, if you remember, based on Thomson's model, we do have neutral particles. Okay, so the proton must be counteracted by the electron in equal amounts. So our electrons are equal. And then mass number, based on our equation right here, is your protons plus your neutrons, because those are the two massive particles. Electrons don't count. So our mass number here is 18. Okay, and our abbreviation is up. So looking at that, and this is where it kind of comes in, the mass number isn't one single specific number. We'll talk about this a little bit more, but there's something called an isotope where there can be different mass numbers for the same atom. Okay, which is why we use the proton number to identify our atoms, because that number will never change. Oxygen always has 8 protons. Okay, if it changes, then it becomes something else. All right, so next one, we don't know the atom, but we are given the proton number. So if you treat that as your atomic number and look for the big 33, you'll find arsenic. Okay, and then again, all atoms are considered neutral, so 33, 33, and then to find our mass number, we add the 33 and the 42 because the protons and the neutrons are what actually contain mass, and you get 75. And this does match your periodic table where it says 74.9. Okay, and last one, we're looking for P, or atomic number 15, which is phosphorus. And if you go through, we know that we have 15 electrons, and then this one we have to go with the mass number that's written on our periodic table. Phosphorus says 30.9, so we round mass numbers. If we're talking about individual atoms, we always write those as whole numbers. So we're going to round that to 31, which would make our neutrons 16. Okay, we'll talk about isotopes too, and that'll make sense as to why the numbers on the periodic table aren't whole numbers. Just a little bit of fun to end with. Don't forget to bring in notes to class and to do your online assignment, but Chemistry Cat has a few little quips related to atomic structure.